Go back to 2013 for me real fast. So we got here. Remember how we got here? Where did we get these values from to plug in? Our previous icebox. So we actually solved for X from the total pressure. Remember, total pressure had nothing to do with the Kp value. Total pressure was just equilibrium pressure plus equilibrium pressure plus equilibrium pressure, which was 1.26, which they gave us. So don't forget, you can always, this is Dalton's law, the law of partial pressures, and then we solve for X to be the amount of two products made in terms of their partial pressures. Remember, none of this is concentration, so everything's in atmospheres in terms of the partial pressures. We plugged in Kp, and we said, those of you, see Clayton here, for this one on that like webinar I watched, they said if you put brackets here, you will not get your credit for Kp setup because brackets mean concentration, so you have to use your partial pressure setups. On part D, it asked, the temperature of the equilibrium is increased to 425 Kelvin. What will the value of Kp, or sorry, will the value of Kp increase, decrease, or stay the same? So they told us the fact that it was endothermic earlier on, right? Remember at the very top, we wrote down all of our givens, and one of them was delta H is positive, it's endothermic. So what happens whenever I increase the temperature? Which way does it proceed?
More thermodynamically favorable.
Okay, so it favors, so whenever you are expressing it, that's a good way to describe it. Increased temperature will favor the endothermic direction, which is the which direction in this case? The forward, right? So you would say the forward direction is favored, and you can describe, you can string these things together. Let's give you some thoughts here. Forward direction is favored. So if the forward direction is favored, what would happen to the K value? Increase, decrease, stay the same. Increase, but why? Thank you. There's more products. So that would increase the K value because more products. And don't put because like that. You have to write out because in your reaction or in your actual answer. Because more products formed. And then the second part of this said, part E said, and another experiment, the original partial pressures of each of those guys are 1 atmosphere each at 400 Kelvin. Predict whether the amount of SO2, Cl2 in the container will increase, decrease, or remain the same. What was the very first thing you had to set up here? If they gave you everything was 1 atmosphere. Help me out here, guys. So maybe the Q though, right? So K is reserved for talking about equilibrium. This is saying initially we have 1 atmosphere for each of these. So that's our Q value. Q is equal to partial pressure of, what was it, SO2 here, Cl2 here, over PSO2, Cl2. And you absolutely have to label these because they said you wouldn't get full credit because they won't know which is which. So make sure you label this whenever you're writing your K expressions out. So then you can put 1 atmosphere over 1 atmosphere. Well, guess what? Q is equal to 1. How does that compare to KSP? I mean, the KP that we just got.
Smaller.
Right. So this is smaller or less than KP, which we had in part C to be 2.2, I believe. So then if it's less than, if Q is less than K, which direction does it proceed? Forward. So you have to proceed forward. So since Q is less than K, and your calculation support should show that, then forward direction is favored. So then what would that do to the partial pressure of SO2, Cl2? What happens to SO2, Cl2 if you're proceeding forward? It decreases because it's a reactant, so it's consumed. So the SO2, Cl2 actually didn't say pressure, it just said amount, right? Yeah, sorry, it said amount. So you can just say SO2, Cl2 is consumed, so therefore it decreases in the forward direction. Okay, that wasn't too bad, right? That question in particular wasn't in part E, got you 2 points because you had to find the prediction of the forward direction being favored, meaning find your Q and see that it's less than K, that was 1 point. And then the fact that SO2, Cl2 was decreasing because it was getting consumed is another point. Okay. Next one, 2010, was the one that you guys had to draw the isomers. What was one version of the isomer? What did it look like? straight chain, carbon, 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 carbon. Another one would be a branch chain, meaning like, I'm not going to draw every single part of this, but you'd have H's all the way around there. That would be our linear or straight chain one. And then maybe one like this, with H's, of course, everywhere to make 4 bonds. So that would be a branch chain. That would be considered like an isobutane. So we have our 2 structures. There really wasn't another way you could draw. Oh, no, you could draw. No, you really couldn't. Never mind. This has to be a pen. So that's about it. You got 1 point for each structure. Okay? Labeling it N-butane and isobutane. Part B stated, on the basis of molecular structure, identify the isomer that has a higher boiling point. Which did you guys say? N-butane or iso had the higher boiling point? Why N-butane? So which would you say, the branch or the linear has more area? Linear structure, right. So the linear structure has it has stackability, basically. So what you can say is that there's more surface-to-surface contact in N-butane on N-butane versus the branch structure limiting the amount of surface contact from the isobutane structure. So the more surface-to-surface contact, the more induced dipoles. What do I mean by that? LDS, right. Induced dipole moments is the term used to also describe London dispersion forces. So increased London dispersion forces would therefore increase the physical property of boiling point, but due to the more attraction. So they try to ask you to, minimize your explanations. Don't write like books for them. They don't have time to read all that. And then most of the time when you write more, you actually end up contradicting yourself, and then they don't give you your points. So make sure you're kind of using your words wisely. Part C, write the KC expression. Given the N-butane equilibrates to iso, how did you write the expression? What on top?
Isobutane on top.
Okay, so K is the isobutane concentration on top over the N-butane. Okay, we all know that that's N-butane. Okay, so that got you a point for KC. And then part D said to solve for, given the moles of N-butane, 1 liter container, 25 degrees C, calculate the initial pressure when N-butane is first introduced. So what did we use here? Say in? P equals RT, right. PV equals RT. So you knew everything except for P. So you solved by plugging in the 0.01 mole, so 0.0821 liters per mole K, 298 Kelvin over 1 liter. So you should have gotten P to be 0.24 atmospheres, because why did I limit to 2 sig figs? Who had 2 sig figs in your problem? The 1 liter actually, and the N value, right? The mole value is 0.01010. So that should be our pressure of our N-butane. That got you 1 point for the pressure there. Part E, N-butane reacts until equilibrium has been established at 25 degrees C. Calculate the total pressure in the container at equilibrium. Anybody have a quick answer for me here? Strive, did you get this part? We're on part E, I. I'm gonna call on you guys. You guys gotta help me out on your board tiers. So every mole, so good. So he said pressure stays the same because there's every 1 mole of reactant consumed, there's 1 mole of product created, and they're both in their gaseous phase. So it doesn't affect the pressure because there's the same number of molecules overall net. So that's basically what I said. The pressure at equilibrium remains constant because for every molecule of N-butane reacting, there is 1 molecule of isobutane formed. Pressure is equal to 0.24 atmospheres still. And it says calculate there. So you could have shown like BDA was subtracting of 1 mole and adding of 1 mole, and it would have been net the same. But they should give you credit for this statement like that we just said. Part II said calculate the molar concentrations of each species at equilibrium. Lewis, did you set up this one?
No.
Did anybody give me a starting point here? This is EII. AC is equal to, so they told us 2.5, right? We got that from earlier. And then what? So we're equaling X over
0.1 minus X.
0.01 molar minus X. So tell me what this means on.
We showed the KC expression.
Okay. And what's this X on top representing?
Isobutane.
Okay, so you're saying N-butane equilibrates to isobutane. N-butane, everybody knows from the example given. We start off with this many moles per 1 liter, which is that in molarity, right? Same story. And this was 0 at the beginning of the icebox. And then what did you guys do?
Subtract X on
Okay, and added it here, right? Okay, so at equilibrium, we have 0.010 minus X, and this is just X, that's what they plugged in right here, products of reactants. And then you can solve for X, and can you neglect X here? No, you want to. No, because this is a 2.5, not small at all. So make sure you multiply across or plug in your solver, whatever you need to do. So 0.01 minus X times 2.5 equals X, and then combine like terms, and then divide, solve for X. So anybody get X for me? Okay. I got 0.007, is what you said, 0.07143. Okay, but we need to look at our sig figs. This X is representing iso, right? So this is the concentration of isobutane. How many sig figs would we need there? 2. Well, and I actually want to make you look at the math here. We'll do 2.5. So we'll do 2.5 times this, and then equals X. So when you manipulate this down, you get like 0.025. You let this subtract. Because one of them it was dealing with decimals, but we'll work on sig figs later. So you will round this to 171 molar for iso. And then what was the N-butane, or what would you have to do? Yeah, so we're just going to plug that in and subtract. So 0.010 minus 0.0071 molar gives us, this is the one where we have, there's 3 decimals. Because there's 3 decimals here and there's 4 decimals here. So the 3 decimals, when you subtract, sig figs don't really count. It's the decimals that count. So you'll do 3 decimals in the end, not really sig figs. So this would give us 0.0029, which we need to round to 0.003 molar, which would be our N-butane concentration. And then part triple I. If the volume of the system is reduced to half of its original volume, what will the new concentration of N-butane be after equilibrium has been reestablished? Anybody have a guess for me? Take a stab at it. If we half the volume, well, first of all, what's happening to K? Well, you say they're the same. Possibly. So it would be 2 times, only because at equilibrium, since it's not shifting, right? Because the volume change doesn't affect equilibrium. What's the only thing that really is going to? Well, the volume change is not affecting equilibrium. Why? There's a reason here. When does volume affect equilibrium? Right, and we have 1 mole of it on each side, so there is no shift here. So, but the volume is still affecting the concentration only because if the equilibrium's not shifting, the moles are the same. And if the moles are the same, that's cool. But if you decrease the concentration by half, it doubles the decrease the volume by half, it doubles concentration. So, for example, let's do N-butane. That's N-butane, yeah. So if this is what it is, moles per 1 liter, if you half the concentration, that's going to be same number of moles because no shift occurred over 0.5 liters, and I'm just kind of making up the number here. But what's that going to be when I multiply by 2? Because remember, this is like divided by half. It actually looks like multiply by 2 would be 0.06 molar. So the concentration does double from its original form. Okay. And then part, so you got 1 point for that question. So if you got it wrong, no big deal. 1 point's not that bad. Part E, suppose blah, 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 blah. Oh, no, this is a good one. Okay. So in all this situation, we were talking about N-butane equilibrating to form isobutane. Now the situation is opposite. You're starting with 0.01 mole of isobutane and placing it in 1 liter rigid container, and it's coming to equilibrium, it says what's the concentration of all the species in the at equilibrium. Do you guys remember that no matter what the scenario is initially, they always end at the same equilibrium conditions if it's that reaction at a specific temperature? So it doesn't matter if I'm going from here, equilibrium to form product, or product, equilibrium to form reactant, vice versa. It doesn't matter what I initially start with, they always have the same equilibrium concentrations no matter what. That's an easy point if you can remember that versus you working it out the entire way. So basically, if it's the same reaction, the temperature is the same, the K is the same, correct? Well, the only way the K is going to remain the same is if the ratio of reactants to products or products to reactants is the same. So that's why the ratio has to stay the same. If I'm starting off with 0.01 mole, it's going to equilibrate to the same value. So the values are the same. 0.0071 molar iso and 0.003 molar in butane. Yeah, values are the same. And you can explain that, or you can actually work in the icebox and figure it out yourself. It's just more work that way. Okay, jump to 2011 for me. And we can quickly answer these. We have ethyl methanoate and we have liquid ethyl methanoate put into a container containing argon gas at 1 atmosphere, 20 degrees C. The pressure in the container was monitored for 70 seconds after the ethyl methanoate was added. Some of the liquid remained. You can see the volume. I mean, you can see the pressure versus time graph right below that. So part 1, explain why the pressure in the flask increased during the first 60 seconds. Shannon, what you got?
I said it was moving towards equilibrium.
So what's forming at equilibrium? Okay, so the vapor. So you have to relate, like in this question, you had to say liquid was evaporating to vapor or gas. Because liquid doesn't cause pressure. You have to note the fact that there's a gas forming. So some of the liquid ethyl methanoate is going to vapor phase and colliding with container walls to cause pressure. If you can ever reference the fact that particles are colliding with the container walls, that'll give you your full points for pressure. So that should be 1 point. Part 2, explain in terms of processes occurring at the molecular level while the pressure remained constant after 60 seconds. Jack.
Because after 60 seconds, there's still liquid left. The pressure in the container is the same as the boiling point of the liquid at its given temperature. So it won't evaporate.
So what are you saying it has met? Equilibrium. So you have to mention equilibrium someplace there. I'm going to add to that though because Shannon just mentioned the fact that there was an so part CI. Yeah. Part CI, we said that increased pressure was caused to increased rate of vaporization, and then the vapors increased pressure due to collisions with the container wall. So to add to that discussion to say that we are at equilibrium now, we're going to say the rate of vaporization equals the rate of what? Condensation. And that's going to allow for the pressure to net the same because it's dynamic equilibrium, meaning it's going back and forth, back and forth, back and forth, evaporating, condensing, evaporating, condensing, evaporating, condensing, because there's still liquid there, that's why it can occur. But specifically mentioning that and the fact that it's at equilibrium, so the pressure is going to remain the same, is going to be 2 points to note in that question. You'll give your full points. And that's, is this chemical equilibrium or physical equilibrium? Physical is about phase change. Okay, and then part triple I, at 60 seconds, what's the value of the partial pressure of ethyl methanoate? How do you guys do that one? So what's the total pressure according to the graph?
1.25.
1.25 atmospheres was our total pressure. And then what'd you do? Right. It was one atmosphere, right? So this was simply a subtraction problem, but they love to do it from data, from a graph, or from data tables. So it's P total minus P of argon equals P of ethyl methanoate, blah, blah, blah. Okay, so that should be 1 point for the partial pressure there. And then part 4, at 80 seconds, additional liquid methanoate is added to the container. Does the partial pressure of it increase, decrease, or stay the same? Zonky, what'd you say?
I would say remain the same.
Why remain the same?
Because the equilibrium rate reach, you want to change it.
So, but I'm adding pure liquid. Does it cause a shift in equilibrium? Because this is a reactions like what? Ethyl, I'm not going to write out the formula. Okay, so ethyl methanoate liquid equilibrates to ethyl methanoate gas. If I increase the liquid, does it cause a shift? No. Stick with your first answer. I'm just testing you. Okay, why would this not cause a shift? Pure, right. If it's a pure solid, liquid, or pure solid, it does not affect the concentrations at equilibrium. So increasing a pure liquid will cause no shift. That's one way to note it. If there's no shift, there's no change in equilibrium conditions, so there's no change in partial pressure. Also, vapor pressure a compound has a specific vapor pressure at a specific temperature. Did the temperature change? No. So what you can state is the temperature is not changing, the vapor pressure is not changing, therefore the partial pressure of blah, blah, blah is not able to change at this condition. So both of those would work. But I think the temperature one gives you more information about like your knowledge of chemistry, because they basically said on the webinar, like if we feel like your student does not know what they're talking about or does not express their knowledge of chemistry with the question, no matter if you're beating around the bush, they won't give you credit because they want to know that you know what you're talking about. So as much chemistry as you can vomit on the paper, people, do it. Okay, part 2009. Let's do this real fast. We just set this one up. Molar concentration. 2009. How did you? So you guys, I know, wrote down all your givens because you always do, right? 14 grams of the, what is that? Ethylamine. Ethylamine. Okay. 500 milliliters. So what does that mean? Oh, that means later on you're going to be limiting to 3 sig figs. Probably, right? 4 sig figs, 3 sig figs. And the first question says, what's the concentration? So how'd you guys set that up? Okay, so you took your 14.85 grams to moles. And I know it's stupid, but please show your work there because they need to know how you got where you're going. So you guys get 45.09 grams. Okay, so that's, you actually got 1 point for this. 3293. I can't read my writing because that's you got for your moles. Maybe you didn't stop there. Maybe you went straight on divided, but they would have given you a point for inferred moles. So you should have gotten this many moles of your ethylamine, and then you would have divided by what? 0.500 liters. I know. I know you did. So this would give you and how many sig figs would I record here? 3.659 molar. Okay, and that's ethylamine. Okay, there we go. So you got 1 point for moles and 1 point for concentration. Yeah. You good? I thought you had your hand up. Okay. So KB, how'd you guys set up KB? Go for it. KB. Isn't that the next question? Yeah. So they give you the reaction, okay? KB would be whatever what? Concentration. The protonated, okay? Or the protonated. This is the conjugate. This is the conjugate acid, right? OH minus over ethylamine 2. And that, you have to put your charge there and your plus on your. So the KB should have been set up just like that, no water. If you put KQ, that covers the gamma. Yeah. They did note, this was weird, so I'm glad you asked that. They said if you put KA, of course you've gotten it wrong. Like they would not give you credit because it's not. I'm not asking.
What if we just put K, just in case we only put K, we don't put anything else?
You're not contradicting yourself, so you're good. Whatever you do, don't contradict yourself. You take your point that you earned. Just put K. But if it says to solve for the K, oh, it doesn't say. It just says solve for equilibrium constant. It says they solve for KB or K. Put that individual there. Okay, part C, which is higher? Which is higher, guys?
C2H5NH2
Why?
because it's a weak base.
That does not tell me why.
Because weak bases don't react much. Weak
Weak bases
dissociate.
Don't, what?
It doesn't dissociate.
Don't, what kind of dissociate? Okay, I can be fully, or you can say 100% dissociate. So leaving, and you might want to add to that. So that's going to be it, because weak bases don't fully dissociate, leaving more of the ethylamine than product made, right? So that's than conjugate acid made, and you can note that. So they said, you get a point, because that's basically what I said. They said weak bases have a small Kb value, meaning partial dissociation in water. Therefore, more of that than that. But I think you get your full point there. Part double I, is that where we're at now? Yeah, double I. This is the reaction. How do acids and bases react? What's the only thing that happens between them? One proton is exchanged, and that is it. Don't go crazy, people. Okay, so ethylamine. And what's the acid reacting with here? HCl, but HCl is the acid reacting, but once HCl drops in the water, what has it formed?
H plus 3O+.
Okay, so, or I'm going to go with water and H plus together, H3O plus. And I think that's the easier way to write these. Now, you can put H plus there, so it'll give you points for either this or this. You could put Cl, HCl. I think it will make life a little bit more difficult for you, so I would choose one of these two reactants and go with the flow. So this one, H, bad acid. So we have a bronzed acid donating its H plus there, H plus, and then water is formed, and then equilibrates to just that with an H plus, right? C2H5NH3 plus. So this one, to me, is I think you're more familiar with because you've seen this same semi format like that. You can do it that way too. 1 point for a full NIE. Part double or part I. Oh, sorry, I did part double I first. Part I, how do you find the concentration of OH?
14 minus the pH equals the POH.
So 14 minus.
10.93.
So you guys saw the 10.93 was given in the question, and this is talking about the solution formed. It's not about the initial base. It's about the solution formed after this reaction has occurred. Okay, so that's important to note because the rest of the problem is going to relate to that solution being formed, not the originals at all. So when you subtract your 10.93, you get POH to be what? 3.07, and then you found your concentration of OH being how? 10 to the negative POH. So set that up, so 10 to the negative 3.07. And these equations are on your reference sheet, of course. You do have access to that. I think you know your stuff. So you guys got 8.5 times 10 to the negative 4th molar as your OH. Yes? Okay, so do circle your stuff, box them up so that they know that what your final answer is. They shouldn't have to hunt, and they won't. Everybody good there? That's 1 point for getting your hydronium concentration. Okay, here's the big boy. Triple I. Calculate the molar concentration of the conjugate acid that is formed. How did you guys set up? I think mine's a little long, but I can't think of another way to do it right now. Anybody have a good starting point here? What do you say? If you did an icebox, what would go as your reaction? But those would be your acids and bases, right? Okay, so this is a big point of contention. Iceboxes go with reactant and water. Iceboxes do not go with reactions. Okay, iceboxes always go with the dissociation of a weak acid or a weak base with water. Never, 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 never do we put a reaction, a true full-on reaction here. And we actually have a whole reaction. It's an acid-base reaction. Notice I did not put equilibrium errors. You guys would not have gotten full credit. Oh, dude, I did put equilibrium. That's not supposed to be equilibrium. This is a good arrow. This is not. Because these are reactions that go forward. They're favorable in the forward direction. They usually go full 100% forward. Same thing here. So this is the reaction I'm going to transcribe and put in a, not an icebox, but in a EDA. That's how I'm starting. So I'm going to just pretend that's down here. You guys would have started with how many? Oh, sorry. Iceboxes use what unit? Molarity. BDAs use moles. So before we start this, we got to get moles, right? So they gave you concentrations of 0.5 of the ethylamine and 0.5 liters. So what's 0.5 times 0.5? Say again. 0.25. Okay, so that's 0.25 moles of the ethylamine. And then strong acid, they gave you 0.2 molar HCl and 0.5 liters. So how many moles is that? 0.2 times 0.5. 0.1. 5 times 2 is 10. Bounce it back twice. 0.1. So that I'm just pretending my reactions here, okay? So who's my LR? The strong acid added, right? So this one's my LR, this one's my excess. I'm making this guy in water.
Wait, do you have to show our work for getting moles?
You do. I would. 100% would. And I did at the very beginning of this problem, but I just didn't write it again. Okay. So then LR, you get 0 that's left over, you subtract here. And this one's an easy one because it's a 1 to 1 to 1 to 1 ratio. So what are you doing here? In the during? Subtracting 0.1, okay. Yeah, subtracting there. So you get 0.15 moles of that left over, which may not be important. Maybe I'm going to fill it out anyway. And then this product made, I start off with 0 and 0 both these. I'm adding 0.1 moles there as well. So that's going to give me 0.1 moles here. But this is what I'm looking for, right? Is that what I'm looking for? What's the question? Molarity. That's not what I'm looking for.
Divided by 0.7.
So where'd you get 0.7?
Or the added together milliliters of the.
No, it's 1.
It's 1 liter, right? Where did we
Yes,
get
it
1
is.
liter? Oh, because it's 500. Yeah, so it's 500 milliliters plus 500 milliliters. So you need to divide this by 1 liter to give you 0.10 molar. Okay, so if you put 0.1 moles, you would have set up all this. You would have gotten a point for your. So what they did was they give you a point for your setup here, because they know that that's hard. You know, M times V give you moles. They give you points for getting up your moles there, and they give you moles down here for your final answer. So if you got that far and then divide by 1 and showed your work to get to molar, then you wouldn't have got your final point. Okay, and then part quadruple I before, it says it's all for, what's the KV? How do you find the KV?
Henderson Hasselbalch.
Okay, let's do that. Henderson Hasselbalch, what's the formula? If we're doing Henderson Hasselbalch in base form.
POH equals PKB plus bond. The conjugate base over.
Conjugate acid over weak base? Okay. So don't forget when you do your Henderson Hasselbalch in a base form, it's OH, KB, and that's capital K. Okay. And then it's always regarding your weak base or your weak acid if it's the acidic portion on the bottom, and it's the opposite one on top. So in this case, what do we know? You know, the POH was like 3.07, I think was that from the very beginning, part B. PKB will solve for momentarily, equals plus log of, what's the conjugate acid?
0.10.
This guy, yep. And that's, it's okay for these to be in moles or molarity. I'm just going to record it in moles. So I'm looking at this and this. I know it's divided by 1 liter, but I'm just describing to you again. You can always put moles in your Henderson Hasselbalch over 0.25 molar, or mole. And then, so find your log, subtract. How do you add a K, or how do you get out of P? Oh, sorry. I'm thinking that is a 1. It looked like a 2.
It was 0.7.
Thank you. Okay, so calculate by taking 3.07, subtract this log thing, and then how do you get out of KB?
You 10 to the negative PKB equals KB.
Okay, so same thing as doing like 10 to the negative pH or POH. PKB is just the function 10 to the negative. So we'll take this number and do it 10 to the negative, because 10 to the negative PKB cancels out the P part and gives you just the KB. And I did mine slightly differently. You guys tell me what you get.
I got 5.62 times 10 to the negative 4th.
Okay, I'll show you guys my way too, because that's basically what I got. 5.6 times 10 to the negative 4th equals your KB. No units. So the way I think Henderson Husband might be easier the way I did it. I did KB expression that we just wrote in part part B, and I plugged in my OH concentration that I had already calculated, and I put in my concentration that I just got in part III for my conjugate acid over the 0.15 molar for the conjugate base remaining, same answer. So you just plug everything in your KB expression as well and get KB. Okay, yes. Oh yeah, smell pretty. Okay, let's set up 2010 then together. I know you guys haven't gotten that far. Ready? Oops. Oh, yeah, I'll do that in a second. 2010. Read it. Read the beginning. Tell me the givens. I don't care that it's cream colored, okay? Read the 2010. What's important? So very insoluble is our is our silver bromide, okay? 298K. All right, everybody tell me how to set up part A. Part A, write the expression for the solubility product constant.
Plus times constant.
Okay, so why no denominator?
Because that's a solid. Solids.
Right, so we're thinking of this being a solid equilibrating to its two ions, and this one's an easy 1-to-1. What if it was like silver sulfide? Yeah, so if it was like silver sulfide, you would have what? Right, so you'd have two silver ions plus sulfide, like that, and you'd have to have Ag squared there if that were the case. But this is a 1-to-1, so we're easy peasy. Calculate the value of silver in 50 milliliters of a saturated sample. How would you guys do that? Give me a quick setup. This is again 5 times 10 to the negative 13. Says, okay, so this would be x squared because these are made in a 1-to-1 ratio. Okay, and then what? Okay, so we square root x is 2.5. Nope, lives. I always want to do that. Square root of 5 is not 2.5. 7.1 times 10 to the negative 7th molar. And you're saying that's silver's concentration? Yes? Okay. Why did they tell you 50 milliliter sample? To confuse you. It's not necessarily confuse you. It's more to say, do you remember that molarity is an intensive property? Meaning you can have a cup of the concentrated Kool-Aid or an ocean full of it. It's the same concentration. It's just a little bit or a lot of it. But this is the same scenario. I can have 50 milliliters, I can have 500 milliliters. The concentration itself doesn't change. It's an intensive property. It's an inherent characteristic. Which maybe will help you with part C. 50 milliliter sample of distilled water is added to the solution described in part B, which is in a beaker with some solid silver bromide at the bottom. The solution is stirred and the equilibrium is reestablished. Some solid silver bromide remains in the beaker. Is the value of Ag plus greater, less than, or equal to? Why equal those?
saturated.
Okay, so there's some precipitate snow saturated because still saturated solution at the same temperature, right? The temperature didn't change at 298 Kelvin. Okay, I can go with that. Concentration of silver is equal because it's still saturated solution there. Anybody add to that? What happens when you add water? What's going to happen to the silver sulfide sitting on the bottom of the container? Right, you're going to essentially, I'll walk you through this process here, okay? You're essentially going to be diluting these. If you add water, lots and lots of distilled water, you're diluting those. Oh my gosh, what happens? Huh? So these are diluted. You decrease the concentration of these. Is it going to shift? Yes, the chateliers has been, or the equilibrium has been disturbed. These now being diluted means you need to shift to the right to make more of these ions. If you shift to the right and you make more ions, what seems to happen to molarity? Okay, so you're putting together the fact that you've made more ions over more volume. So more ions over more volume, the ratio is still the same for molarity. So you could describe it that way and say, despite the fact that the water added causes a shift to the right to increase the solubility, that's divided by a similar ratio of liters of solution, so the molarity remains unchanged. Or you can say that molarity doesn't depend on volume. You can say it's an intrinsic property. You can kind of say still saturated saturation has a specific molarity at a specific temperature. A lot of those phrases will give you your points here. Part D, calculate the minimum volume of distilled water in liters necessary to completely dissolve 5 grams of silver bromide. And they give you the molar mass. Tell me how to start. So what's our question here? So units. What are the units is looking for? Liters, right? Liters of solution or liters of water? Water. Okay. We're going to assume most of this solution is water. It's really, 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 really dilute. What's our starting point then? Okay, so like you can probably see they're leading you to use the 5 grams because then what do they give you in parentheses? The molar mass. They want you to do what with the grams? Convert to moles. They're really trying to help you. They're not evil people. Sometimes. Okay, so I think we all can convert to moles. So 1 mole of silver bromide is 188 grams of silver bromide. Okay, so I got to moles. How do I get to liters? In the concentration you got in part B, right? This is part B. This is part C, sorry. So you're going to use this, and how do I write it? So 7.1 times 10 to the negative 7th moles of silver bromide are dissolved per 1 liter of solution, and that solution, again, is mostly water. It's a very dilute sample. So we get 3.7 times 10 to the 4th liters. Who would have thought to go all the way through that if you thought about it for a minute? I mean, if they start you with 5 grams and they gave you the molar mass and you just calculated the molarity, I think the pieces fall into place. But you can't let yourself get stuck on something like this. This part's not hard. The first point came from converting dissolved to moles, and the second point came from getting your final by use of your molar solubility that you found in part B. So it was contingent upon you using your part B answer. And part part E. Read that one for me. And tell me how to proceed. I'm going to give you about 30 seconds. Read part E. Go for it. Okay. Yeah. So, how would you know for precipitate forms? So, if Q is greater, what does that mean? And so, products in this case are ions, right? We're like, oh no, too many ions. So what happens? It shifts back to the left and would precipitate. So how do we find Q? Get me started. How do we find Q? Let me see if you guys can get me there.
That silver nitrate. You just multiply.
What do you mean you multiply?
Multiply times something negative 4.
That's molarity of silver nitrate, not silver.
We have to find the molarity with the increased liters.
Thank you.
Milliliters.
That's the part where everybody gets caught up. Okay, so there you would simply look at the question and go, oh, there's a molarity of silver, there's a molarity of bromide, multiply. But you would not get any points there. You might get a final conclusion point, but that's not it. You must dilute your samples. Okay, so that means you must do M times V over V total to get your new molarity. That's what I mean. You need to write this down. Okay. Everything here, basically for this whole packet, will probably be 2 test grades based on the amount of practice we do. So make sure you're with me so I can always take up your stuff and give you a credit grade. So we're going to do the molarity diluted for both samples. So silver would be, what's the milliliters of silver? Of the silver nitrate? 10. So I'm going to go in millis the whole way, if that's okay. 10 milliliters times, I think this is what you said, 1.5 times 10 to the negative 4 millimoles per liter. Sorry, per milliliter, because that's milli over milli. Or use moles or liters, I don't care. And what's the total sample there?
12.
12, okay. That's per total of 12 milliliters, because it was 10 plus 2. And you'll notice all these millis will cancel, giving you moles per liter in the end. So the silver concentration is 1.25 times 10 to the negative 4th molar. So there's silver ion. So you guys tell me, if we're doing molarity times volume over V total, this is just like the dilution equation, of course. And 1V1 equals M2V2. Tell me how to set for bromine. Milliliters? 2 milliliters times. So this is the molarity of silver bromide, 5 times 10 to the negative 4th millimoles per milliliter over 12, our total again. And that's going to give us our bromide concentration of, I got your calculation, 8.3 times 10 to the negative 5th molar. So now that we have silver ion and bromide ion concentration in the new diluted situation, thank you, Clayton. Don't forget to dilute. How would you find Q? Now multiply these, right? So Q is still the same setup. Silver initial concentration after dilution, of course, times bromide initial concentration after dilution. So you guys can plug those boom times boom to give us 1.04 times 10 to the negative 8. All right, so that's Q. 1.04 times 10 to the negative 8. What are you comparing that to? Which is what?
5.0 10 to the negative 13.
KSP is 5.0 times 10 to the negative 13. Okay, so what can you conclude? Well, tell me what our, who's greater? Okay, so in your statement, you need to state that. Okay, because it's supported by calculation, but Q is greater than KSP. So, what's the student going to observe? Okay, so precipitation occurs as equilibrium is reestablished. And that's a good way to state it because we need to precipitate the ions out to reestablish equilibrium with the appropriate ratio of concentrations. You can say that there's also too many ions in solution causing a shift left, which will cause precipitation to occur, but that's kind of what I'm saying with this reestablishing equilibrium, because shifting is under reestablishment of equilibrium. Okay, last one, guys. Part F. The color of another salt of silver, silver iodide, is yellow. A student adds a solution of sodium iodide to a test tube containing a small amount of solid cream-colored silver bromide. After stirring the contents of the test tube, the student observes that the solid in the test tube changes the color from cream to yellow. Write the chemical equation for the reaction occurred in the test tube.
First off, let's do that. What's happening in the test tube? What are the reactants? So, say again?
Silver iodide and silver bromide.
But think about that. Can those two react? It's going to be sodium, right? If you read it closely, I know I just read that out loud. What should give you a hint there is it tells you that the test tube changes from cream to yellow. So what is present initially and what forms at the end? What's the cream colored one? So silver bromide has to be in there in the beginning. And who has to be there in the end? Silver iodide, the yellow one. Okay, so that should say to you the two initial and final. So we know that silver bromide is here to begin with. We know silver iodide is here to end with. Well, who react with silver bromide? Sodium iodide. And then what's made in addition to silver iodide? What kind of reaction is this, people? Double replacement. Okay, double replacement. So who's the other product? Sodium bromide. Okay, so you knew this was our cream colored one that we had to begin with. You knew this was the yellow one that we had to end with. So our reaction should be that cell balance 1, 1, 1, 1. I don't know if you have to denote the states of matter, but you definitely could put like precipitate over here. But the next part states which salt has a greater KSP value? KB? Silver bromide or silver iodide? Give me your best guess. Who has a greater KSP value? So if you have a greater, so think back. If you have a greater KSP value, what does that mean about you? So if this is great, then you form more ions than precipitate. And I'm gonna say that means you're more soluble, right? Okay, so if you're more soluble than the other one, what does it mean the other one's doing? Precipitating. So tell me who's going to have a greater KSP. Silver bromide, because it actually is not precipitating in the end. If it were, if it has a greater KSP, it's the one that's more soluble. And the one that's more soluble is the one that's not precipitating. So you have to say silver bromide because in the end, if it were less soluble, it would never react. Like it would be like, nope, can't react. I've got to remain a precipitate. I will halt this reaction because I cannot dissolve. This one is the one doing that now because it's like, oh, silver bromide, you're more soluble. You can react. You can form the silver iodide, which would force the reaction to occur. It's the driving force of reaction. So KSP, KBr is greater than AGI. Yeah. All right. Thank you for your participation today. I need a couple more things from you. Yeah.
I was just going to ask, what was for D for 2010? What was?
Is that the? I'll go back there and say this thing. Let me make a split-second decision on what I need you to do. Do you guys see the multiple choice in this packet under Big Idea 6? It starts on page 52. Okay, so I want you to do the multiple choice, which they're random, okay? They're like 26, 30, 40, 55, and so forth. So I want you to start with that, and it ends on page 54. So they're just those couple right there. There's 1, 2, 3, 4, 5, 6, 7, 8 multiple choice. And then I want you to do, I have to pick wisely here. Do the next two 2011s and stop there. Okay? So you got 2 FRQs and 8 multiple choice. You might be able to knock out a couple multiple choice right now, but the 2 FRQs are what I definitely want. And tomorrow, I'll finish those other ones later because there are 4 FRQs left, and I'm just going to let you guys do half of them. I'll finish the other ones later. So tomorrow we're going to start kinetics. So if you can get some kinetics outlined, maybe not all of it, but some of it. And then tomorrow we'll kind of kick it back into Connects seem to be on your knowledgeable at things, a little bit less memorable. So a lot of you are like, I forgot all the kinetics. So if you can finish those 2 FRQs, those 8 multiple choice, start looking at kinetics, I'll be happy. That seems like a lot unless you want to work on the FRQs. But I want to check these FRQs. Equilibrium is a big deal, so I want to make sure that we're okay. I have open B, because I have duty A. Yeah. Okay. I'll do the other FRQs later with you guys. Go team. Thank you. Yeah, like 5 minutes. Announcements will come on shortly. What is this? Oh, this is your homework. Oh, Nathaniel, I'm going to tell you the answer. Hold on.
Oh, I already got it.
Thanks, Donkey.
I just filled in the holes where I didn't know what you said.
Keep all your stuff together. Keep all your stuff together. Yes, sir. Okay. Yeah, you definitely want to do that.